think I'm a bit of a technological determinist. I think that our innovations often occur when certain technologies are in place that can allow them to happen. Arguably the web occurred when our hard disks were big enough to store interesting numbers of images, and the networks were fast enough to communicate those images. The work we did on the grid occurred when high-speed networks were such that one could reasonably outsource computing to remote computers. They were thinking of computers as something that would exist as a utility that would provide large amounts of capacity to them when they wanted it. And so that's where this term grid computing came from, which sort of evolved a little bit after Globus, I would say. The notion of computing as something that you could plug your applications into and get access to the data or the software or the compute power that you needed to do whatever it is that you wanted to do. It turns out that's not it's not a new idea. The utility computing was the term I think was first coined in the early 60s by a guy called John McCarthy, the AI pioneer, who was working on a thing called Project Mac at MIT, and the first time-sharing computer. And he said at that time, computing will be, in the future we'll have computing utilities, just like a water utility or a sewage utility, a computing utility. You'll be able to plug into it and get whatever power you want. Computing was done either on these workstations, which are of course somewhat underpowered, very underpowered relative to today, and then various so-called supercomputers at different locations, each of which was quite different than any other in its operating system and operating environment. So one ended up spending a lot of time negotiating the vagaries of the different network protocols and operating systems that existed. So a lot of the work we did in grid computing in the early days was working out how to connect things together, how to federate computers at 10 or 100 or 1,000 different locations. What's happened over the last 5 years in particular has been this notion of computing as a utility has really been effectively monetized, commercialized by the likes of Amazon and Microsoft and so forth, which is very exciting. What I'm interested in particular right now is how do we leverage this new cloud computing paradigm to accelerate discovery in the sciences. And one way we're doing that is taking a lot of the logic that, and the software indeed, but the logic that we used to encapsulate in software and give to people to deploy on their own computers in order to manage, for example, large collaborative virtual organizations, and turning them into services that can be accessed over the network, running on cloud computers. So Globus is somewhat evolved from it's still a set of protocols for connecting things together, but instead of being delivered to people as tarballs, software that you would download and install and struggle with on whatever peculiar computer you had of your own, you can now access over the network, just like many commercial cloud services. So that's been a lot of work, but it's really transformed, I think, how we're able to provide capabilities to researchers. We initially called it Globus Online, now we just call it Globus. Grown very rapidly to like 15,000 users. We decided if we're going to work out how to outsource activities to the cloud, we should start with something very mundane and simple that no one, or very few people, want to be concerned with. So we decided to take on this task of data movement, because it ended up being one of the most important uses of Globus, was simply managing the movement of data between the many nodes of a computing grid or a research collaboration, moving data from a scientific instrument like a genome sequencing machine to an analysis computer and so forth. Negotiating the security, authentication, identity, management protocols, the network protocols, the firewalls, etc. So our first Globus cloud service was simply something to which you could outsource the task of moving data from one place to another. So we're now at the point where we've moved 50 petabytes, 3 billion files. If you want to move data reliably and securely and rapidly from A to B, so there's complex security things to negotiate when you're dealing with supercomputer centers and genome sequencing centers. That's one thing. Secondly, if you're trying to move 100 gigabytes or a terabyte or 100 terabytes, inevitably things will fail along the way. Disk servers will get overloaded, the network will get overloaded, someone may chop a wire, there may be a power outage, any of 100 things can happen. And so one has to be able to respond to those, detect and respond to those problems. And so a lot of the logic in Globus transfer, as we call it, is about detecting and responding to those sorts of problems. We have protocols that can restart transfers where they left off. We have restart markers built into our protocol so we can detect how far we've got at any one point in time. It's technically fascinating, but it's something that's like plumbing. You want it to work. Why are we interested in moving data? It's because we want to accelerate discovery processes that depend on many other things, not just moving data, but computing on that data, discovering it, allowing people to collaborate around the processes that will take data and turn it into knowledge. So I think the opportunities that we're starting to explore now are how do we outsource many of those activities to cloud computing resources as well. So that's, I think, where the excitement lies in the future. And that then starts to, as you start to do that, start to explore those problems, and you're starting to look at how may the processes of science itself, the processes of discovery, change. Do we end up in a more collaborative, collective, big science approach to more problems? Problems not just in the physical and biological sciences, but also in the social sciences.